Hello, I'm Mr. Rickers. Today we're going to learn about something that a lot of students have trouble with, prime factorization. To start off, we should look at some definitions, the word factors, the word product, prime numbers, composite numbers, and then we'll look into finding prime factorizations. The objectives of today's lesson: finding factors of a number, identify prime numbers and composite numbers, and then finally, find prime factorization. First objective, find factors of a number. When it doesn't say prime factors, we're looking for all factors. So we need to understand what factors are. The numbers that are being multiplied in a multiplication problem are called factors. The answer is called the product. For example, the product of 3 and 4 can be written with a symbol, multiplication symbol that looks like an X. It can be a raised dot, such as 3 times 4 equals 12, or it can be parentheses. All three of these mean the same thing. 3 times 4 equals 12. In this example, the 3 and the 4 are called factors. We're not going to differentiate between multiplicand and multiplier. And then the answer in the multiplication problem is called the product. Any questions? Okay, let's move on. So this first example here says find all the factors of 60. So what I'm going to do is look for pairs of numbers that when you multiply them together, they equal 60. Well, we can always start out with the number itself and 1. Now, I happen to know that 60 is an even number, so I can it's divisible by 2, so I should be able to find a product with 2 as a factor, and then the other factor would be 30, so 30 times 2. We can also divide by 3, and we would get 20 times 3. We can divide by 5, we would get 12 times 5. Divide by 6, 10 times 6. And I believe I've covered all the bases. So the answer to this problem would look like this. I'm going to write them in ascending order. 1, 2, 3. I knew I forgot one. There is another one. 4 times 15. So 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. All the integer factors of 60. Okay, moving on. Second objective in today's lesson, identifying prime numbers and composite numbers. Whole numbers that have only 2 factors are called prime numbers. They can only be divided evenly by themselves in 1. Prime number is a whole number that has exactly 2 different factors, itself and 1. So as an example, I'll use 5. The only way that I would be able to write 5 as a product of 2 factors would be the number itself times 1. And this is the only way that I can write 5 as a product of 2 factors, so it's prime. Now looking at composite numbers. Now we have to keep in mind that 0 and 1 are special cases and they're neither prime nor composite. So on to composite numbers. A number that is not prime is called a composite number. The numbers 0 and 1 are neither prime nor composite. So let's look at, for example, 15. Well, of course, I can write 15 as a product of itself, 15 and 1, but I can write it as a product in a second way, 5 times 3. Since I can find 2 different pairs of factors for 15, 15 has to be a composite number. Okay? Let's look at this example to illustrate. Now 0, as I mentioned earlier, is a special case. So Neither. Our goal here is to identify the numbers as prime, composite, or neither. So I will just write down prime. I'll abbreviate composite, COMP, or neither. Okay. 2 is a prime number because the only way that we can write 2 as a product of two numbers is itself in 1. So it's prime. And in fact, 2 is the only even prime number, as we'll see. Now, for a number to be prime, it has to be a whole number. 2.5 is not a whole number. And again, for it to be a composite number, it has to be a whole number. So 2.5 is not a composite number either. So this would be neither. All right, looking at 3. Of course, we can write 3 as a product of two factors, 3 times 1. Can you think of any others? Nope. 3 is a prime number as well. Now 10 is 10 times 1, but also we could write it as 5 times 2. This makes 10 a composite number. Okay? All other prime numbers other than 2 are odd numbers, so we would expect or suspect that any odd number may be a prime number. For example, 11 times 1, but there is no other way to write 11 as a product of two numbers, so 11 is prime. On the other hand, 21 can be written as 21 times 1, but also 7 times 3. So even though it's an odd number, some of the odd numbers are not prime numbers. This example is composite. 31, the only way we can write it as product is 31 times 1. So it's prime. Same with 41. Now my question for you, 51. Of course, 51 times 1. Think of any other examples? May not be entirely obvious, but it's also 17 times 3, which makes 51 a composite number. So hopefully I'm explaining well enough that you understand the difference between prime numbers and composite numbers. Moving on. Find prime factorization. To be able to go through the process of finding the prime factorization of a number, you'll need to memorize at least the first 15 prime numbers or so. They're listed below. 2, 3, 4, 5, 7, 11, 13, 17, 19, 23, 29, 31. And I generally tell my students that's enough. But let's move on and look at these others. 37, 41, 43, 47. Now this list is actually an infinite list. This just shows the first 15. Okay. It's very rare to have to use prime numbers greater than these in these type of problems. Okay. Notice here that the only even number in this list is 2. Then we have odd numbers 3, 5, 7. What about 9? No. 9 is 9 times 1. Also 3 times 3. So we exclude 9 from the list of prime numbers because it's a composite. Okay. Several more things you'll need to know. Divisibility rules. Okay. First one, the divisibility rule for 2. Okay. What you do is ask yourself, is it an even number? If your answer is yes, then it's divisible by 2. For example, 46, an even number, we could divide by 2, and we would get 23 times 2. Okay? So 46 is divisible by 2. How do you know if a number is divisible by 3? I would call this the divisibility rule for 3. Let me give a little bit of an extreme example. How about 456? Most people can't just look at that and know that it's whether or not it's divisible by 3 or not. What we do is add the digits together, So we would take 4 plus 5 plus 6, which is 15. By adding the digits together, you will always get a smaller number than what you're starting with, and should be able to mentally decide whether that sum is divisible by 3. In this case, 15 is divisible by 3. That means the original number, 456, is also divisible by 3. So that's the divisibility test for 3. Next one, and only the first 3 prime numbers have easy divisibility rules like these. The next one would be 5. Ask yourself, is the last digit in your number that you're looking at a 0 or a 5? If the answer is yes, then it's divisible by 5. If no, then it's not. For example, 4560 would be divisible by 5 because the last digit's a 0. Okay, we're going to be applying these rules as we find the prime factorization of various numbers. Moving on. All right. A prime factorization of a number is a factorization in which every factor is a prime number. Okay? So to be able to do these type of problems, sometimes it's helpful to go ahead and list out the first 10 or 15 prime numbers, which I'll do. 2, 3, 5, 7, skip 9, 11, 13, skip 15, 17, 19, skip 21, 23, skip 25, skip 27, that's 9 times 3, 29, 31. 99% of these type of problems, this will be enough, okay? So let's look at this first example. This one we really don't even have to do any work. Why? Prime or composite, 21. As I just mentioned, it don't fit in the list of primes because we could write it as 21 times 1 or 7 times 3. So 21 is not prime. That one's out. Here, look at choice C, 9. We skipped 9 as well. 9 times 1 or 3 times 3. 9 is composite. That one's out. The only choice that's left has to be the correct answer. 3 squared times 7 squared, or 3 times 3 times 7 times 7. Now this is a good time for me to mention the different formats here. 3 times 3 times 7 would be expanded form. 3 squared times 7 squared would be exponential form. Okay. Sometimes the problem will specify which form that they want the answer in. Okay, moving on. Remember the divisibility rules for 2, 3, and 5. We start with 34, and I'll do what I call a prime factorization tree. Okay? 34. So I'm going to do the divisibility rules for 2, 3, and 5, and then if that doesn't do it, then I'll move up the list. So we want to start out trying to divide by the smallest prime numbers and then move up as we run out of choices. Well, since 34 is an even number, I know I can divide by 2, so I'll go ahead and do that. Okay? It's a good idea to always, when you're doing a prime factorization tree, to write your prime numbers on the left side, so at the end of it, the prime factorization, you can get it from the numbers on the left side. Now, when we divide 34 by 2, so I'm just doing long division here. 1 times 2 is 2. We subtract. 1, bring down the 4. 2 will go into 14 7 times. 7 times 2 is 14. And the remainder is 0. So 34 is 2 times 17. Now notice that the number that we ended up with after the division is one of our prime numbers. So if after the division you have a prime number, you're done. 34 is 2 times 17. And that would be the prime factorization of 34. Okay, look some more examples. Of course, they like to give you more difficult problems, so bigger numbers, 189. Again, I'm going to do the prime factorization tree. Okay, so we'll start out. Let me list these again. Okay, we want to start out trying to divide by the smallest prime number, and then if that doesn't work, go on to 3, and then go on to 5, and so on and so forth. Is 189 divisible evenly by 2? The test says if it's an even number, then we can divide by 2. Well, 189 is an odd number. 2's out. Okay? So we try to divide by 3. The divisibility rule for 3 says add the digits together. So 1 plus 8 is 9, plus 9 more is 18. $18 is divisible by 3, so 189 has to be divisible by 3 also. I'll go ahead and put the 3 down, and then go ahead and divide. 1 is not big enough for 3 to divide into it, but 18 is. Okay, 3 goes into 18 6 times. 6 times 3 is 18. When we subtract, we end up with 0. Bring down the next digit, 9. And 3 will divide into 9 3 times. 3 times 3 is 9. When we subtract, we get 0. So the other factor is 63. 63 is again divisible by 3. And when we divide 63 by 3, we get 21, which is also divisible by 3. Divide 21 by 3, we end up with 7. 7 is one of our prime numbers, telling us that we're finished. This right here represents the prime factors of 189. Expanded form, we could write 3 times 3 times 3 times 7. Or exponential, since there are 3 3's, we would write 3 to the 3rd power times 7. That is the prime factorization of 189. Okay, another example, 200. We'll start out trying to divide by 2. It's an even number, so I know I can divide by 2, and we can all do that in our head. 100. 100 is still an even number, so divide by 2, and we'll get 50. 50 is still an even number, 2. 25. Okay, now we have an odd number, so we're done working with 2. Now we try 3. 2 plus 5 is 7. 7 is not divisible by 3, so 25 is not divisible by 3. That one's out. 25 ends with a 5, so we know it's divisible by 5. And when we do so, we end up with 5. 5 is one of the numbers in our list, so we know we're done. So the prime factorization of 200 would include 3 2's and 2 5's. Don't forget to include the last one. That would be the expanded form, or 2 to the 3rd power times 5 to the 2nd power. Exponential form. Notice this instruction here says use exponents when repeated factors appear. That's another way of saying write your answer in exponential form. Okay? One more example. Now we have a lot bigger number, 1,701. Okay, again, we're going to try those prime factors in order from smallest to largest. 1,701 is an odd number, so 2's out. Let's try 3. What we're supposed to do to decide whether it's divisible by 3 is add all the digits together. 1 plus 7 is 8, plus 0 is 8, plus 1 is 9. That sum is divisible by 3, So 1,701 is also divisible by 3. Okay. Now, typically, we would have to do long division. Since I've already worked this out, I know that 1,701 divided by 3 is 567. Okay. Since I was not able to divide by 2 at the beginning, I will not be able to divide by 2 any time later either. But I still need to try 3. 5 plus 6 is 11, plus 7 more is 18. 18 is divisible by 3, so I know 567 is divisible by 3 as well. Okay, so divide 567 by 3. Probably have to do it the hard way unless you're using a calculator. Okay, we'll get 189. So we go on trying 3 until it won't work anymore, and then we would move on to 5. Is 189 divisible by 3? Let's check. 1 plus 8 is 9, plus 9 more is 18. We already decided that 18 is divisible by 3, so 189 is also divisible by 3. And we divide by 3, we get 63. 6 plus 3 is 9, a multiple of 3, so we can divide 63 by 3. And when we do so, we get 21. 2 plus 1 is 3, an obvious multiple of 3. And when we divide 21 by 3, we get 7. 7 is one of our numbers in the list of prime factors, meaning we're done. All we lack is the answer. Okay, notice the instruction again, use exponents. So I'm going to have 1, 2, 3, 4, 5 3s, 3 to the 5th power, and 1 7. That's the exponential form for the prime factorization of 1,701. All right. So you may be wondering, why do we need to know this? That's a normal question for students to ask. Why do I need to know how to write the prime factorization of a number? Well, the answer is this. There are a bunch of different types of problems that it'll help with. Here's some examples. Simplifying a fraction or writing a fraction in lowest terms. One of the ways that you can do that is to write the prime factorization of both the numerator and the denominator. I've already worked it out. 352 is equal to 2 times 2 times 2 times 2 times 2 times 11. 640, I've worked that out as well. It's equal to 2 times 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 5. Now, if you're using this method to simplify a fraction, you don't want to use exponential form. Go ahead and use expanded form like I've done here. Once you have this written out, cancel like prime factors 1 for 1. So I got a 2 both in the numerator and the denominator, so I'll cross that one out. It actually leaves a 1 when you do that. And then another set of 2's, and another set of 2's, another set of 2's, another set of 2's. Now I still have more 2's down here, but no 2's in the top 2 cancel with it. No 11's in the denominator, and no 5's in the numerator. So this means we're done. All I have to do now is to multiply everything back out. Well, I have a whole bunch of 1's times 11, which is 11. And 2 times 2 is 4 times 5 is 20. So 352 over 640 is equal to 11 over 20 in simplified form. That's one example. Here's another example, finding the GCF or greatest common factor and the LCM or least common multiple of 45 and 75. Okay, so we would start out by finding the prime factorization of each of our numbers that we're looking at. Okay, 45 is same as 3 times 15, and 15 is 3 times 5, and 5 is prime, so the prime factorization of 45 is 3 times 3 times 5. 75, it's an odd number. Let's try 3. Well, it is divisible by 3, leaving 25. 25 is not divisible by 3, so we'll try 5. We know it's divisible by 5. And when we divide 25 by 5, we end up with 5. 5 is a prime number, so this one's done. Okay, first of all, let's look at greatest common factor. Very simply, you identify the factors that are in each expansion. Okay, both expansions have at least 1, 3, and both of them have 1, 5. Now, notice that the prime factorization of 75 has only 1, 3, so I can't do another 3. And the prime factorization of 45 only has 1, 5, so I can't do another 5. So the common factors are 3 and 5. I'll write it down. Multiply what I got. The greatest common factor of 45 and 75 would be 15. Least common multiple of two numbers. You start out the same way. Write the prime factorization of each of the numbers that you're looking at. But then you do something different than greatest common factor. What you would do is just write down each of the prime factors you see anywhere once. I see 3s, I see 5s, so I'm going to write them each down one time. Then for each of the numbers that you've written down, go back and find the greatest number of times it shows up in any one spot. 3 shows up twice in this prime factorization and once in this prime factorization, meaning the greatest number of times it shows up is twice. So I'm going to put an exponent of 2 on the 3. Now for 5, in the first one it shows up once, in the second one it shows up twice. So I'm going to put an exponent of 2. The greatest number of times 5 shows up in any one spot. Now we'll multiply this out. 3 squared is 9. 5 squared is 25. And so we end up with 9 times 25, which is 225. The least common multiple of 45 and 75 would be 225. Okay? Why do we want to know least common multiple? Because when we add fractions, we need to have the least common denominator before we can add. Okay? So the least common denominator means the least common multiple of the denominators. And we just did for 45 and 75, we did that already, which is 225. So I'll go ahead and write that down. Now I compare the denominator of my new fraction with the denominator of my original fraction and figure out what I need to multiply the original denominator by to end up with a new denominator. The easiest way to do that, divide 225 by 45, and we would get 5. So we need to multiply 45 times 5. We do the same thing to the top. Okay, this is called the identity property for multiplication. 5 over 5 is 1. Anytime you multiply any number times 1, you end up with the same number. Now in this case, 20 over 225 does look different, but it's the same number as 4 over 45. Now 225 divided by 75 is 3, so I would need to multiply by 3. Do the same thing to the numerator. The effect is that we're multiplying by 3 over 3, or 1. So what I'm going to write over here is going to be the same number as 7 over 75. It just looks different. 7 times 3 is 21. So once we have done that, we have a common denominator. Now, typically students will skip this step, but I'm going to mention it for emphasis. When we add these two fractions, we do not add the denominators. We keep the denominator the same, but we do add the numerators. So we would end up with 20 plus 21 over 225, which is 41 over 225. As always, you need to check if you can simplify your fraction at the end. This one, since 41 is a prime number, cannot be simplified. So that would be the answer. 4 over 45 plus 7 over 75 is equal to 41 over 225. All right, that is the conclusion of my lesson over prime factorization.